This is part 1 of Lecture 8 of Elec 5300. We'll be talking about estimating the autocorrelation. Suppose that we have a random process x of t. We're going to assume that it's ergodic, and we assume that it has an unknown autocorrelation rx of tau. And so we'd like to estimate this rx of tau from data. So suppose that we've measured some data, which we assume is a sample of the random process from time 0 all the way up to some time t, big T. One way we can estimate this autocorrelation is to say, well, the autocorrelation is just the expected value of the product of the random process at time t times the random process at some time shift t plus tau. And so what we can do is, for this particular random process, we can multiply the process here at time t and t plus tau, and then we can try to average it over time because of the fact that it's ergodic, and so time averaging is equivalent to ensemble averaging. So we can take this one and multiply it by that, and we can shift it a little bit, let's say to this time here, t1, and then we can look at another time shift here, t1 plus tau. And we can do that all the way up to this time big T minus tau, because in this case here the time shift is tau and we can't go beyond that point. So we can integrate all the way from here up to here of the product. And then the question is, well, in what sense is Vx of tau a good estimate of Rx of tau? So we've already looked at one measure of quality, and that is unbiasedness. In other words, what we'd like to show is that the expected value of the estimate is actually equal to the thing that we're trying to estimate, in this case, Rx of tau. This is easy to prove using a similar technique as we showed before, just switching the order of integration and expectation. So this is just the definition of the Vx of tau from the previous page. I take the expectation inside the integral to get this. Now this is the autocorrelation of x, Rx of tau, and then this is independent of t. So when I do the integral, I just get big T minus tau times Rx of tau. The big T minus tau cancels with this one in the denominator, and I just get Rx of tau. The other thing we'd like to have is that the variance of Vx of tau should go to 0 as the amount of data that we collect, which is determined by big T, goes to infinity. It turns out that this problem is not so easy to solve, but for Gaussian random processes, it turns out that we can prove the following bound on the variance. Right, so this tells us that at least we can bound the variance, and that bound goes to 0 as t goes to infinity, as long as this integral here integrates to something less than infinity. And so the proof can be found in these two sources here, but let's just take a look at a particular example of what this really means. So let's suppose we have a Gauss-Markov process, Rx of tau is equal to a decaying exponential. We can substitute that into this equation over here, and when we do that, we get 4 divided by big T, the integral of sigma to the 4th, since we're taking the square, e to the minus 2 beta, absolute value of tau. And we can take the sigma squared outside, and we integrate e to the minus 2 beta tau, and we get 1 over 2 beta. And so, simplifying that, we get this expression here, and this depends on two things, right? It depends on beta and tau, and beta and t. And so, of course, we already noted that the larger t is, the better the estimate, so the smaller the variance, or at least the smaller the bound on the variance should be. The question is, how much t do we need? And that depends on beta, right? So the larger the value of beta, right, the faster the process changes, right? So the faster the process changes, then the less time we need to observe the process in order to get a good estimate, right? Because the faster the process changes, basically the faster the process becomes uncorrelated with itself, and it's kind of like we're collecting nearly independent information about the process. However, if beta is very small, right, in which case the process changes very slowly, then even if we look at the process over a relatively long amount of time, we're not really getting independent information about the process, and so that's going to make the variance decrease slower than we would expect it to if we had nearly independent information about the random process. So let's look at a concrete example of this. If we have a Gauss Markov random process, how much data do we need to estimate the data autocorrelation within 10%? And so here by 10% accuracy we mean that the standard deviation should be within 10% of the peak value of the autocorrelation. In other words, the variance divided by the peak value of the autocorrelation squared, right, because the variance is a squared statistic, so sigma to the fourth should be less than 0.1 squared. And by our previous result, this is satisfied if 2 divided by beta t is less than or equal to 0.01. And so therefore the amount of data we need is t is equal to, t at least must be greater than, so we multiply this by t, 200, so we divide by 0.01, 200 divided by beta, right? So as long as t is bigger than this value, then the upper bound here will be smaller than the desired value. And so we take the smallest value of t, which is just this. And so 1 over beta is like a time constant in the process. It kind of tells you how quickly the autocorrelation decays. And so we need about 200 time constants in order to get about 10% accuracy. Okay, so in the next part of the lecture we'll look at estimating the power spectral density.